In today's lesson, we're going to be looking at two more discrete probability distributions, and we'll be looking at the hypergeometric and the negative binomial distributions. And these are going to supplement the discrete distributions that we've already seen. So we've already seen the Bernoulli, the geometric, as well as the binomial distribution. And so adding on both the hypergeometric and the negative binomial are going to start to round out the discrete distributions that we're going to look at. In the next lecture, we will look at the Poisson distribution, which will be the final discrete one that we look at before we move on to talking about continuous probability distributions. So just like we wanted to understand the binomial distribution, in this lecture, we want to understand the hypergeometric distribution, its use cases and properties, and the negative binomial distribution, its use cases and its properties. And so we'll start again with different examples here, right? So in the first example, if you imagine instead of a manufacturing line where you're producing different say phones, which you could test whether they're functioning or not without breaking the phone, you could imagine working in, say, a chemical manufacturing plant, where in order to test the batch for whether or not it's up to quality, whatever quality means, you have to actually sample and destroy that part of the sample, right? And so in this case, we're doing sort of a sampling without replacement of sorts. The probability are going to be shifting in that way. And so because of that, we're into a different scenario than we were looking at with the binomial distribution. In another way, you could think about, say, working in oil fields. And if you've done a sort of preemptive scan and suggest that there's several different spots that you could start to drill, and you want to know if I start to drill in any of these, which of them are actually going to have oil when we begin to drill, then you're working with something that looks a little bit like the geometric distribution, but maybe you don't want to stop at one success, right? Maybe you want to say, how long until we find 5 different oil spots from this preliminary scan. Right, and so both of these scenarios are going to end up being captured by either our hypergeometric or our negative binomial distribution. So the hypergeometric distribution is going to be sampling from a finite population without replacement. Each time it's going to be success or failure, just like we've been looking at up till now. So we'll still assume that there's a fixed number of trials, n. We'll assume that there's some total number of items in the sample, which we use capital N for the population size. And we assume that a fixed number of these are going to be successes, which is, say, n successes. Then we say that the random variable x, which looks at the total number of successes, follows a hypergeometric distribution with the 3 parameters, big N, m, little n, right? And what we're doing is we're counting the number of successes in a total of n samples, right? So you could think about this as drawing cards from a deck of cards where the successes are going to be the aces, right? And so we have 52 total cards. There are 4 items, which are successes, and then we could set a certain number of trials. Maybe you draw 13 cards. We're going to have closed form expressions for the expectation, the variance, and the probability mass function. So the expected value is going to be little n times by the proportion of successes, m over n, right? And so this looks a lot like the binomial distribution in a way, right? If you think about what's the probability of success on the first draw, well, that's going to be m divided by n. And so if you take m over n to be p, then this is still n times p. With the variance, you can see that we have this term out front, n minus n over n minus 1. But then we have n times what looks like p times 1 minus p, right? Where again, m over n is what we're thinking of as p. And so this term out front is what we would call the finite population correction factor, right? When we were looking at the binomial distribution, we had said if you're sampling without replacement, then it's not going to be quite right. And this is why it's not going to be quite right. The PMF is going to be expressed purely in forms of combinations. So it'll be m choose x times by n minus m choose n minus x divided by n choose little n, right? And So we have sort of these closed formed expressions, and we can use it anytime that we're sampling without replacement. Now, just to clarify my point about the relationship to the binomial distribution, note that if we take p to be m over n, then as we saw, the expected value is going to be n times p, and the variance is going to be that term out front times n times p times 1 minus p. This is, again, almost exactly identical to the binomial distribution, except now we have this extra multiplicative term, and we call that the finite population correction factor. If you take big N to be tending towards infinity, so you're working on larger and larger samples, then that term is going to tend towards 1, right? And this shows why the binomial can approximate sampling without replacement, right? If big N is way larger than small n, if you're taking a sample of size 10 out of a population of 1 million, then that's basically just going to be 1, right? And so because of that, as we get into larger and larger populations without changing how big of a sample we're taking, then we can use the binomial distribution. And it tends to be a little bit easier to work with the binomial distribution than the hypergeometric. Now, the negative binomial distribution is still going to be working with these repeated Bernoulli trials. And we're going to count the number of trials until successes, except instead of, like in the geometric distribution, instead of counting until the first success, we want to go until the kth success. So we assume that we have some fixed number of successes to observe, which we'll call R. There's some constant probability of success, which is P. Each of the trials are going to be independent of each other, so the exact same setup that we're used to working with here. Then we would say that the random variable x that counts the number of failures before the rth success is going to be distributed as a negative binomial Rp random variable. Once again, we can write down the expected value, the variance, and the probability mass function. So the expected value is going to be R, which is counting up till the rth success, times 1 minus p divided by p. The variance is going to be similar, except we're dividing by p squared. And then the PMF is going to be x plus r minus 1, choose r minus 1, times by p to the r, 1 minus p to the x. Right? And so this is sort of a generalization of the geometric distribution. But instead of just counting up until the first success, we want to specify r successes, right? So we can think about this as we're going to start flipping a coin, and I'm going to keep flipping the coin until I get 10 heads. And then if we want to know how many times did I end up having to flip the coin in total, or how many tails did I see during that period of time, that's going to be captured by the negative binomial distribution. If you set r equals 1, this is just the geometric distribution, right? So counting till the first success, that's just exactly how we defined the geometric distribution. Now, we often care about just reaching the first success, right? Oftentimes after the first success, the process is going to be over. And so that's why we sort of treat that separately. But in the general case, you can always just work with the negative binomial instead of the geometric distribution. Like the geometric distribution was, sometimes we're going to include those R successes in the total number of trials. And so then instead of counting the number of failures, we count the total number of trials until the Rth success. But then you're just shifting everything by that value of R. So there was a very quick run through of, again, another 2 discrete probability distributions. So the hypergeometric distribution is going to characterize the number of successes when we're sampling without replacement, rather than the binomial, which would be sampling with replacement. The hypergeometric distribution relies on the assumptions of a fixed finite total with a fixed number of successes and a fixed number of trials. The negative binomial distribution counts the number of failures until we achieve a set number of successes. The negative binomial relies on the same assumptions that we've seen. And both distributions are going to have closed form PMFs, expectations, and variances. And so we can work with them to do probability calculations, to do expected value calculations, and the same thing. In the next lecture, we're going to look at one last discrete distribution before we start moving on to thinking about continuous probability distributions. And so I hope to see you all there.